Hello, and welcome to the video lecture for topic 13, SN2 reactions of alkyl halides. So the SN2 reaction is a one-step transformation that replaces, or more appropriately said, substitutes one of the groups on an sp3 hybridized carbon. Right? So to begin, I'd like to just lay out and define some of the terminology, right, that we're going to be using for this topic. So first of all, this term SN2. So SN2 stands for substitution nucleophilic, and then the 2 stands for bimolecular. So what this means is that in the reaction, there's a substitution happening. One thing is being replaced by something else. The nucleophilic tells us that whatever is being replaced by a nucleophile. And then the 2 tells us that overall in this reaction, the rate determining step involves 2 different molecules colliding with each other. Okay, so that starts us off. Now we need to get a little bit deeper with this nucleophile. What is a nucleophile? So the word nucleophile literally means nucleus loving, right? Or more accurately, we can think of this as a nucleophile is nucleus seeking. It is a species, right, that is going to be a Lewis base, so it's going to be an electron donor that is looking for something that has either a positive charge or a partial positive charge to make a bond with. Now that thing that's got the positive charge or the partial positive charge has a specific name for us as well, and that's known as an electrophile. Electrophile. And an electrophile, it literally means electron loving, but more appropriately, right, we would think of this as it's something that is seeking an electron. So our nucleophiles are always going to be a Lewis base, which means that they are an electron pair donor. And our electrophiles, while they won't always be in Lewis acid, sometimes will be in acid, right? They're always going to have either a formal positive charge or a partial positive charge, right? So one of those two. It's either going to have a formal charge of +1, or there's going to be a polarized bond, and we're going to have a delta plus on some atom in the molecule. So when an sp3 hybridized carbon atom, right, is bonded to a more electronegative atom, so for example, a carbon halogen bond, right, it is that carbon halogen bond is polarized because the halogen is more electronegative. So if I have a carbon atom, here I'm just going to bond it to a chlorine atom, right? We know that chlorine's electronegativity is significantly higher than carbon's electronegativity. This bond is polarized in this direction. And so we can think that we can assume, or we know that this carbon atom is going to have a partial positive charge, and this chlorine atom is going to have a partial negative charge. The bond is polarized in this way, which means that this carbon fits our definition of an electrophile, right? It is electron seeking, it has a partial positive charge, it's looking for it's looking to get some more electron density, and so it's ready to react with some sort of a nucleophile, right? Some sort of a Lewis base. Right? And so if we draw in some substituents, right, onto this carbon atom, we can think of the SN1 reaction overall, the SN2 reaction overall. We have some sort of a nucleophile. It's got a lone pair, it's a Lewis base. That nucleophile will react with our electrophilic carbon and displace this halogen, right, which we call a leaving group, to give a new molecule and that chlorine ion right, goes off by itself and now has a negative charge, right? So this is the overall one-step transformation of the SN2 reaction. A nucleophile attacks an electrophile to displace a leaving group, right, and generate a newly substituted or differently substituted carbon atom. So I'm going to erase what we've got here and then get into a little bit more details talking about the properties of this transformation. So we said that this SN2 reaction is a bimolecular reaction, but one more thing we need to know is that it's also a single-step reaction. All of the bond making and bond breaking happens at once. So let's take a look at that one more time. Here now I have my carbon atom. It's going to be bonded to a halogen. X is a generic, any of the halogens, just a generic placeholder for us. For now, I'm going to only have hydrogens as my other substituents, and I'm just going to use a generic nucleophile, right, which is a Lewis base. So as we said, this carbon has a partial positive charge. This halogen has a partial negative charge. This bond is polarized in this way, right? And so this partial positive on the carbon, right, attracts, the nucleophile is attracted to that partial positive, and so it begins to approach the electrophilic carbon from the opposite side of the halogen, right? So we don't have the same side approach, but we have an opposite side approach, right? Halogen's on one side of that electrophilic carbon, nucleophile approaches from the opposite side. And since this is a single-step process, the bond making and bond breaking have to happen simultaneously. And so as this nucleophile approaches, right, we generate what's called a transition state. And so our transition state has our nucleophile in proximity to our carbon atom. Here's our halogen, which is our leaving group. We always put transition states into brackets and give them this double dagger symbol. So as the nucleophile begins to approach, right, the bond between the carbon and the halogen begins to weaken, and it goes from a covalent bond to a partial covalent bond. Similarly, as the nucleophile approaches, right, we now begin to form a bond between the nucleophile and the electrophilic carbon. We still have these three hydrogen atoms attached, and what happens as this nucleophile approaches is those hydrogen atoms begin to, as opposed to being a tetrahedral geometry, they begin to become planar, right? And they begin to all sit in the same plane as this carbon atom. Right, so we have all three hydrogens in the same plane as the carbon. This is a planar here with the nucleophile approaching from one side and the electrophile leaving off the other side. Right, so this is our overall, what we would call, transition state for this reaction. Right. So for our arrow pushing, we have our nucleophile forming a new bond to our electrophile. Our leaving group falls off at the same time. And we just have now nucleophile bonded to carbon and our halogen has fallen off as a leaving group. Okay? So the reason we put our transition states into brackets is that it's a very short-lived intermediate. It doesn't sit around for very long, right? It's very fleeting, and we can't isolate it, we can't really observe it, but based on certain properties we know, and certain experimental properties, right, and experimental results, we know or we believe that this is most likely what is occurring. So we now know the general features of an SN2 reaction. We have a electrophile, it forms a new bond to a nucleophile, we lose a leaving group, right? Now I want to go through and really dig into the different parts, the different things that will affect an SN1 reaction. So there are 5 things that we need to consider in the SN2 reaction. We need to consider the electrophile, the nucleophile, the leaving group, the solvent, and the product. And we're going to take a look at each of those one at a time. So let's start with the electrophile. So for our electrophiles, we've seen, right, that when we looked at that transition state just a moment ago, we've seen that in that transition state, the carbon atom has 5 different things that are either bonded or partially bonded to it. That electrophilic carbon has 5 substituents on it, right? And so, as that begins to happen, the sizes of those substituents play a role in terms of steric effects, right? If I have bulky groups attached to that hydrogen opposite of my, on the opposite side of my leaving group, it's going to be very difficult for my nucleophile to approach, right? Those large groups create steric bulk. And so there are only certain types of carbon atoms that can actually participate in an SN2 reaction, right? Those would be methyl halides and primary halides and secondary halides. So let's take a look at each one of those. So our methyl halide, we have a carbon with 3 hydrogens and an halogen. Our primary, we would have a carbon. Here now I'm going to put some other carbon group. I still have 2 hydrogens and a halogen. And finally, for my secondaries, I would have 2 carbons, 1 hydrogen, and 1 halogen. These are the only types of carbon atoms, right, that can participate in SN2 reactions. Methyl alkyl halides, primary alkyl halides, and secondary alkyl halides. Once I get to a tertiary alkyl halide, there is too much steric bulk. So here now I'll draw a tertiary alkyl halide. So here now I have a carbon group, another carbon group, and a third carbon group off of my electrophilic carbon. There's my halogen. At this point, if we consider these to be methyls, right, these methyl groups are so big that they actually block the nucleophile. They create a shield around that opposite side of my carbon atom, and they block the nucleophile from being able to approach, right? That nucleophile is blocked. So tertiary carbons, tertiary alkyl halides never participate in an SN2 reaction. The potential energy in that transition state is too great because of all of the sterics created by these 3 different alkyl groups. So in order of preference, methyl is the best for an SN2. Primary is good for an SN2, and secondary are okay. Once we get to a tertiary alkyl halide, it is a no-go, right? Tertiary alkyl halides do not react by SN2, do not participate in SN2 reactions. All right, so let's take a look now next at the nucleophiles. So for our nucleophiles, right, our next factor that we're going to consider, and I'll refer you to table 6.3 in Sorrel, right, which goes through good nucleophiles, bad nucleophiles, and their properties. But really quickly, the steric considerations that we had with our electrophiles also, in a sense, apply to our nucleophiles. So let's take a look at 2 potential nucleophiles, right? One, we're going to have methanol. So here I have 3 hydrogens, or excuse me, methoxide, and this very nice, strong nucleophile, versus tert butoxide. So I have a carbon with 3 methyl groups, and a negatively charged oxygen. Right? If I compare these two, similar to how these 3 methyl groups on our alkyl halide block our nucleophile from approaching, these 3 methyl groups right here now in our nucleophile kind of surround that oxygen atom and create steric bulk here as well, which would prevent the nucleophile from approaching the electrophile, right? And so this is a good nucleophile, whereas our bulky tertiary nucleophile is a poor nucleophile. Okay? So that's what we need to consider. That's one of the things that we need to consider in terms of our nucleophile, is the steric bulk around the nucleophilic atom, just like we want to consider steric bulk around the electrophilic atom. So the third factor we're going to consider, that's important for us to consider, third of 5, is going to be the nature of our leaving group. So here now we're going to look at the leaving group. Okay? And so our leaving group should be a weak base, right? We want to create a weak base. And the reason for that is because we don't want competition between our leaving group and our nucleophile. So let's take a look at an example. So here now, we're going to have sodium cyanide as our nucleophile. Again, I've got a Lewis base as my nucleophile. And then I'm just going to do methyl bromide as my electrophile. So here are there's my methyl, and there's my bromide. So here now, bromine is my leaving group. So if I want to think which of these two, my nucleophile or my leaving group, is going to be the weaker base, I do my standard pKa kind of an assessment. Now, while you're not expected to know the pKa of hydrocyanic acid, I'm going to tell you right now that it's about 9, right? So the pKa of our conjugate acid here, HCN, is about 9. Now the pKa of our conjugate acid of our leaving group, so that conjugate acid is HBr, and that pKa is about -9. So this is a strong acid, which means our leaving group, right, our leaving group, Br minus, is a weak base. Right? Here our nucleophile is going to be the weaker acid, which means our leaving group, if it were to be a leaving group, it would be a strong base. So we would expect this reaction to be favorable. Now, if our nucleophile is a weaker base than our leaving group, we would expect that if the substitution were to occur, the reaction would just reverse itself, right? Because now my leaving group is a stronger base, right? That my bromide, if this was iodine versus bromine, HI is a stronger acid than HBr. So my Br would be the stronger base, right? And my HI would be a better leaving group. So we need to take, right, our considerations of the conjugate acids of our nucleophile, conjugate acid of our leaving group, see which of those two is going to be the weaker base. So for our example here, bromide is the weaker base. That makes bromide a good leaving group, which is abbreviated Lg. I'm going to say one more thing here. Fluorine is never a leaving group, ever, right? So I'm going to put here F minus, never a leaving group. And the reason F minus is never a leaving group is because it is a strong base. The carbon-fluorine bond is very strong. HF is a weak acid. Remember, the pKa of HF is about 3.3. That makes it, relative to other halogen acids, it's a relatively weak acid. So it's going to be, so this means it's going to be its conjugate base, F minus, is a really strong base in comparison to the rest of our halides. And so F minus is never, ever, ever a leaving group, right? You will never displace a fluorine atom from a carbon atom. Okay, we've got two more factors to get through. I'm going to clean up the board. We'll be right back to look at those. So the last two factors we need to consider for the SN2 reaction are the solvent and the stereochemistry of the product. So let's start off by looking at the solvent, right? So there are two types of solvents that are used in substitution reactions, right? Or that are most frequently used in substitution reactions. So here now we're going to take a look at solvents, right? And there are two types that we need to consider. The first is polar protic solvents, and the second is polar aprotic solvents, right? So our polar protic solvents, these are going to be water or alcohols. So here I'm just generic alcohol, all ROH. And our polar aprotic solvents are again going to be polar solvents, but they're not going to have an acidic proton, right? Water and alcohols both have an acidic proton, but our polar aprotic solvents are not going to have, right, any acidic protons. And so common ones are DMF, which is dimethylformamide, right? So here's DMF. Let's get some better bond angles on that, right? So again, we have a polar solvent with no acidic hydrogen. Another frequent one is known as THF, tetrahydrofuran, right? Again, we have a polar solvent, no acidic hydrogens. And then the other two are acetone and DMSO. And, right, we all remember that's how Sam likes to draw DMSO. Now, one of these is better than the other for SN2 chemistry. And it turns out that polar aprotic solvents are actually much better for us, right? So for SN2, we want a polar aprotic solvent, right, to be what we use. So why is it that we want a polar aprotic solvent versus a polar protic solvent? And this all has to do with the nucleophile, right? The solvent will affect the strength of the nucleophile. So good nucleophiles are some sort of metal ion combination. So we'll take a generic example here. I'm going to use sodium cyanide again. So here now I'm going to look at what happens when I take sodium cyanide, right? So here's my sodium, Na+, here's my cyanide. And I put this into a polar protic solvent. Well, one of the things that happens is that my metal ion, which I want to get away from my nucleophile, right? This is going to be my nucleophile. I want to separate my metal ion from my nucleophile. And a polar protic solvent helps me do that, right? Because we can have these ion-dipole interactions between the oxygen of the alcohol, right? That kind of shield and separate that sodium ion from our cyanide ion, right? So that's a good thing. We've been able to get that nucleophilic group. This nucleophile is now a little bit more exposed. But the problem is that I've got this lone pair here on my nucleophile. And that lone pair can hydrogen bond to the hydrogen of my alcohol solvent, right? And so now that actually ties up that lone pair and makes it more difficult for my nucleophile to go and react with my electrophile. So while this interaction is good, this interaction is bad. and actually makes it more difficult for my nucleophile to form a new bond. So this is for my polar protic solvents. All right, what if I take that same nucleophile, and this time though, I'm going to put it in a polar aprotic solvent. So again, I have my sodium atom, and I have my cyanide anion. Right? This time I'm going to go ahead and use acetone as my polar aprotic solvent. So here now I'm going to get the same ion dipole interaction between my sodium and my Lewis base on acetone. That's going to be my oxygen. So again, I've separated that sodium ion from my nucleophile. My nucleophile is now more exposed and better able to go and find an electrophile, right? It's not tied up in an ionic bond with that sodium. But because I'm using, right, a polar aprotic solvent, no hydrogen bonds can form between my solvent and my nucleophile. So my nucleophile remains exposed. Right? There's no interaction here between the nucleophile and the solvent, or very little interaction between the nucleophile and the solvent, and it is now free from the sodium atom. It is free to go and find an electrophile and react. So this is good, what's happening in our ion dipole interactions, and this is also good that the solvent is not interacting strongly with our nucleophile, and so this is why we prefer polar aprotic solvents for SN2 reactions. All right, I'm going to clean this board off one last time. We're going to look at the last factor, stereochemistry of the product. So because SN2 reactions are a one-step process, also known as a concerted process, and because the nucleophile must approach from the opposite side of the leaving group, SN2 reactions always result in an inversion of stereochemistry, right? So if you start with an R-alkyl halide, you will end up with an S-alkyl halide, and if you start with an S-alkyl halide, you will end up with an R product at the end. So let's take a look at a couple of examples that demonstrate this. So here in my first example, I'm going to use OH minus as my nucleophile, and I'm going to use this here, this alkyl halide, as my electrophile. So here now I'm doing an arrow pushing mechanism. I need to make sure that all of my electrons are present, all of my bonds are clearly displayed, and any formal charges are in place. So my nucleophile does an opposite side approach, reacts with my electrophile, and my leaving group comes off. Now, before anything, before we do the product, let's set the stereochemistry of this carbon atom, right? So my hydrogen, right? My hydrogen is going to be priority 4. My methyl group is priority 3. My ethyl group is priority 2. My bromide is priority 1. Going from 1 to 2 to 3, I'm moving in a clockwise direction. That means that this is an R stereocenter at my electrophilic carbon. So when this nucleophile approaches, right, and the leaving group comes off, that nucleophile actually pushes all of these other 3 groups to the opposite side. So my product would be drawn like this. Here's my carbon atom. There's the nucleophile that I've attached, right? My methyl group goes here, and now my hydrogen is on this side as a hash, and my ethyl group is this side as a wedge. And of course, I make sure to include all electrons in my arrow pushing. Now I have my leaving group, all of the electrons that go with my bromine, my negative charge there. All right, so let's set the stereochemistry here. Well, once again, hydrogen is going to be priority 4. My methyl is priority 3. My ethyl is priority 2. This time, my OH group is priority 1. And if I see now 1, 2, 3, I'm moving in a counterclockwise direction. And this stereo center is now S. Right? Let's take a look at one more example to wrap it up. This time I'm going to use cyanide again, right, as my electrophile, as my nucleophile. But this time I'm going to start with a carbon atom that has a slightly different stereochemistry. So here now I'm going to put an ethyl group up. I'm going to put my methyl group on a wedge, my hydrogen on a hash, and here's my leaving group. I make sure to include all of my electrons. I can do my arrow pushing. Priorities on this group: 4, 3, 2, 1. 1 to 2 to 3, I'm moving counterclockwise. This alkyl halide has an S stereo center. When I draw my products, there's my carbon. That cyanide approached, it pushes the hydrogen and the methyl to the other side of my carbon atom. So now my hydrogen is this direction on a hash. My methyl is this direction on a wedge. My ethyl group I keep on in plane line. And now my new group, now that my cyanide is attached, right, goes to this side. And no mechanism is complete unless it shows the fate of all atoms. So I make sure to include my leaving group with a negative charge. All right, so setting the stereo center now in our product: 4, 3, 2, 1. 1 to 2 to 3, I'm moving in a clockwise direction. This stereo center is R. So SN2 always inverts stereochemistry. Right? And we'll put this in a box here. Right? SN2 always inverts stereochemistry. If you start with R, you'll end up with S. If you start with S, your product will be R. Always, always, always inverts stereochemistry. Okay, so that's what I've got for you on topic 13. I really highly recommend that you also read in Sorrel about what properties make a nucleophile a good nucleophile versus a poor nucleophile. I kind of glossed over that pretty quickly, but there's a lot of good information on that in your reading as well, so I'll refer you to Sorrel for that. And hopefully you have found this video lecture valuable in learning about the SN2 reaction and the 5 major things that we need to be paying attention to whenever we're working with SN2 chemistry. All right, thank you very much, and enjoy your day.